Welcome back, time travelers and sequence seekers. Today, we're diving into the fascinating world of neural networks that remember those that truly understand sequences, time, and context. If you've ever used a voice assistant, enjoyed machine translation, or relied on predictive text, you've already experienced the magic of RNNs and LSTMs in action. These networks are the backbone of AI systems that process information over time, making sense of data that unfolds in a sequence. Join us as we journey through the evolution of memory and artificial intelligence, exploring how these models revolutionize the way machines understand the world. Let's get started on this time-aware adventure. Traditional neural networks have a significant limitation. They treat each input as if it were independent, with no memory of what came before. This approach works well for static data like images, but it fails when dealing with sequences such as speech, text, or time series where context is crucial. Imagine reading a book and forgetting each sentence as soon as you move to the next. That's the challenge AI faces without memory. Recurrent neural networks, or RNNs, address this by introducing memory, allowing information from previous steps to influence the current one. This breakthrough enables AI to understand context and process sequences more naturally. The key innovation behind RNNs is their ability to remember. Unlike traditional networks, RNNs have loops that allow information to persist, creating an internal memory of previous inputs. They process sequences step by step, maintaining a hidden state that carries information forward. Each output depends not only on the current input but also on what came before, thanks to this hidden state. This is like reading a book and understanding each sentence in the context of the entire story. RNNs reuse the same weights at each time step, making them efficient for sequence modeling. This structure is what sets RNNs apart in handling sequential data. RNNs shine in tasks where context matters. For example, in text prediction, the network understands that after "the cat sat on the pho," the word mat is more likely than car. In stock price forecasting, today's price depends on yesterday's trend. In speech, the meaning of a word often relies on the words that came before. These real-world examples highlight how RNNs use memory to make smarter predictions, making them invaluable for applications that require understanding sequences over time. Despite their strengths, RNNs face a major challenge known as the vanishing gradient problem. When processing long sequences, the gradients used to update the network's weights become extremely small during training. This means the network gradually forgets information from earlier in the sequence, much like a message getting lost in a long game of telephone. For example, if a sentence starts with "I grew up in France" and ends with "I speak fluent," the RNN might forget France by the time it needs to predict French. This limitation makes it hard for RNNs to learn long-term dependencies, reducing their effectiveness for complex tasks. The vanishing gradient problem isn't just a technical detail, it has real consequences. Networks that can't remember information from earlier in a sequence struggle with tasks that require understanding context over time. This leads to poor performance on long sequences, difficulty learning complex patterns, and limited usefulness for many real-world applications. Recognizing this challenge was a turning point in neural network research, prompting the development of new architectures designed to overcome these memory limitations. Long short-term memory networks, or LSTMs, were created to solve the memory problem in RNNs. LSTMs are a special kind of RNN designed to remember information for long periods. Their secret? A separate cell state that acts like a conveyor belt, carrying information through the sequence with minimal changes. This cell state is carefully regulated by gates that control what information gets added, removed, or output at each step. Thanks to this design, LSTMs can learn which information is important to keep and which can be forgotten, making them powerful tools for handling long-term dependencies. LSTMs introduce a clever architecture that separates short-term and long-term memory. The cell state runs through the entire sequence, acting as a memory highway. At each step, gates decide what information to keep, what to add, and what to remove. This system allows LSTMs to selectively remember or forget information, adapting to the needs of the task. Think of it as a smart filing system that constantly updates itself, ensuring only the most relevant information is available when needed. This flexibility is what makes LSTMs so effective for complex sequence tasks. The power of LSTMs comes from their gate system. There are three main gates: the forget gate, the input gate, and the output gate. The forget gate looks at the current input and previous hidden state to decide what information to remove from the cell state. The input gate determines what new information to add, while the output gate decides what information to pass on to the next step. These gates work together to manage the flow of information, learning through training what's important to remember and what can be safely forgotten. Imagine an efficient secretary managing a filing system. The forget gate is like deciding which old memos to shred. The input gate is choosing which new memos to file, and the output gate is selecting which memos to show you right now. This analogy helps illustrate how LSTMs dynamically manage memory, ensuring the network always has access to the most relevant information for the task at hand. This smart control system is what enables LSTMs to excel at learning from long sequences. Let's compare RNNs and LSTMs side by side. Basic RNNs have short-term memory and a simple architecture, making them faster to train but prone to vanishing gradients. LSTMs, on the other hand, feature a complex gate system that preserves both short and long-term memory. They require more parameters and are slower to train, but they excel at handling long sequences and complex dependencies. The choice between RNN and LSTM depends on your task. Use RNNs for short, simple sequences and LSTMs for longer, more complicated ones. Another important variant is the gated recurrent unit, or GRU. GRUs simplify the LSTM architecture by combining the forget and input gates into a single update gate, reducing the number of parameters. This makes GRUs faster and less computationally demanding, while still handling long-term dependencies effectively. In many cases, GRUs perform just as well as LSTMs, making them a popular choice for sequence modeling when resources are limited. RNNs and LSTMs are widely used in natural language processing. They power machine translation systems, like Google Translate, generate text for autocomplete and chatbots, and analyze sentiment in reviews. By understanding the context of words in a sentence, these networks make language-based AI smarter and more responsive. Their ability to process sequences is what enables them to excel in tasks where meaning depends on word order and context. In speech recognition, RNNs and LSTMs are the engines behind voice assistants like Siri and Alexa. They transcribe spoken words into text, understand voice commands, and enable real-time conversations. By remembering the sequence of sounds and words, these networks make it possible for machines to understand and respond to human speech, transforming the way we interact with technology. RNNs and LSTMs are also powerful tools for time series prediction. They're used to forecast stock prices, predict weather patterns, and estimate energy demand. By analyzing past trends and learning from historical data, these networks can make accurate predictions about future events. Their ability to handle sequential data makes them essential for any application where timing and order matter. In healthcare, RNNs and LSTMs help monitor patients, process medical signals like ECG and EEG, and even predict disease outbreaks. By analyzing sequences of medical data, these networks can detect patterns that might be missed by traditional methods. Their ability to understand time-based information is transforming patient care and medical research. RNNs and LSTMs are making waves in music and audio processing. They can compose new music, synthesize audio, and recommend songs based on listening history. By understanding the sequence of notes or sounds, these networks create more natural and engaging audio experiences. Their impact is felt in everything from music streaming services to digital instruments. Video analysis is another area where RNNs and LSTMs excel. They're used for action recognition, video captioning, and surveillance systems. By processing frames as sequences, these networks can understand movement, describe scenes, and detect unusual activity. Their sequential memory makes them ideal for analyzing dynamic visual data. Training RNNs and LSTMs isn't always easy. These models are computationally intensive and require large amounts of sequential data. They're sensitive to hyperparameters and can be slow to train, especially for long sequences. Overcoming these challenges requires careful tuning and a solid understanding of the underlying architecture. But with the right approach, the results can be truly impressive. To get the most out of RNNs and LSTMs, follow best practices like using gradient clipping to prevent exploding gradients, monitoring training on validation sequences, and choosing appropriate sequence lengths. Consider bidirectional architectures to capture context from both past and future steps. These strategies help ensure stable training and better performance, especially on complex tasks. While RNNs and LSTMs are powerful, newer architectures like transformers and temporal convolutional networks are taking over many natural language processing tasks. Attention mechanisms, in particular, allow models to focus on relevant parts of a sequence, improving performance on long-range dependencies. However, RNNs and LSTMs remain crucial for many applications, especially where real-time processing and time series analysis are needed. Ready to build your own RNN or LSTM? Popular frameworks like TensorFlow and Keras offer layers such as TF-Keras, layers, LSTM, and simple RNN. PyTorch provides Torch, NN, LSTM, and Torch, NN, RNN, while Fast, AI offers high-level abstractions for quick prototyping. These tools make it easier than ever to experiment with sequential models and bring your ideas to life. If you're new to RNNs and LSTMs, start with simple projects like text generation at the character or word level, stock price prediction, sentiment analysis on movie reviews, or time series forecasting. These projects help you understand how sequential models work and give you hands-on experience with real-world data. As you gain confidence, you can tackle more complex challenges. Tuning hyperparameters is crucial for success with RNNs and LSTMs. Pay attention to the number of layers and units, sequence length, batch size, learning rate, and dropout for regularization. Each of these settings can significantly impact your model's performance, so experiment to find the best combination for your specific task. Watch out for common mistakes when working with RNNs and LSTMs. Avoid using too many layers unnecessarily, ensure your input shapes are correctly formatted, and always shuffle your training sequences. Don't forget to reset states between epochs to prevent information from leaking across batches. Being mindful of these pitfalls will save you time and frustration during development. RNNs and LSTMs represent a fundamental breakthrough in handling sequential data. While transformers have taken over many NLP tasks, RNN variants remain essential for time series analysis, real-time processing, and other sequential challenges. Their ability to understand context across time sets them apart from feed-forward networks, enabling AI systems that truly grasp the flow of information. The real power of RNNs and LSTMs lies in their ability to understand context. By remembering what came before, these networks can make sense of complex sequences, whether it's a sentence, a melody, or a series of events. This context awareness is what allows AI to move beyond simple pattern recognition and towards true understanding. If you're excited to start building time-aware AI, now is the perfect time to dive in. With powerful frameworks and a wealth of resources available, you can experiment with RNNs and LSTMs on your own projects. Whether you're interested in language, music, finance, or healthcare, sequential models open up a world of possibilities for creative and impactful AI solutions. To get started, choose a simple sequence problem that interests you and explore the available tools and tutorials. Practice building, training, and evaluating your models. As you gain experience, you'll discover new ways to apply RNNs and LSTMs to solve problems and create innovative AI applications. Remember, the journey of learning is itself a sequence, each step builds on the last. In the world of sequences, context is everything, and RNNs never forget that. These networks have transformed the way AI understands and processes sequential data, enabling smarter, more responsive systems. Whether you're building chatbots, forecasting trends, or composing music. RNNs and LSTMs provide the tools you need to bring your ideas to life. Thank you for joining us on this journey through time-aware neural networks. Keep exploring, keep learning, and remember, in AI, context truly matters.